At this point, we've looked at voltage generally, and then we also considered voltage within a uniform electric field. For example, between two voltage plates. In this tutorial, we'll look at voltage in regions around point charges, or charged particles. Again, we'll use a gravity analogy, but this time the analogy will involve the Earth and a satellite. Point masses representing our point charges. In this scenario, we're not staying close to the Earth's surface, and therefore we must recognize that the gravitational field strength and related force is going to vary as we look at different positions. The field lines are more dense or stronger as we get closer to our mass or charge. Definitely not a uniform field. So, the gravitational force between these two items would be determined using Newton's general equation for gravity. Switching over to our similar scenario, in the electrical world, we have a negatively charged particle and a smaller positively charged particle here. True that we would have gravitational forces in this scenario, but with such small masses, they would be insignificant as compared to our electrostatic forces. To calculate the magnitude of our electrostatic forces, we would be using Coulomb's law. So let's stop and compare our equations for a second. Both give us a force in newtons. Both of these equations also have a constant, G for gravitational force and K for electrical force. They are both inversely proportional to the distance r squared. Then we have our extra characteristic specific to the masses or the charged particles. Mass for gravity in kilograms and charge for electrostatics in coulombs. Now, we've already spent some time with potential energy comparisons, so we'll list the equations for that and just note that it's in joules for both of them. Again, lots of similarities to notice. We're ready to consider our potential difference. For the gravitational potential of our satellite, we take the mass of the satellite out of the equation. If we take our potential energy equation and we divide out the satellite's mass, we have Vg equals negative Gm over r. So if the unit for EP was in joules and we divide by our mass in kilograms, then our gravitational potential will be, again, in joules per kilogram. So now let's plot some equipotential lines. Along the surface of the Earth, we would have Vg1, and that's minus g mass of the Earth over the radius of the Earth. Out further, 2 radii from the Earth's center, we could have Vg2, minus g mass of the Earth over 2r, and continuing to Vg3, and so on. Again, we notice that this potential value doesn't depend on the satellite's mass. To determine the potential energy of a particular satellite at any of these positions, we simply multiply the mass of that satellite with our gravitational potential. So let's switch over to our electrical charges. Electrical potential difference, or voltage. Like potential energy, but without the charge. So dividing out the charge, and we have V equals kq over r. Let's mark some equipotential lines in our electric field. These lines are always perpendicular to the field lines. If our first line is 1 radius away, then it has an electrical potential or voltage of V1 equals kq over r, and that would be in joules per coulomb or volts. The second, being 2 radii out, V2 equals kq over 2r. The third, kq over 3r, etc. Again, this potential value or voltage doesn't depend on the second charge. For example, let's consider our voltage at this third line. To determine the potential energy of a particular charge at this position, we simply specify the second charge and multiply. EP equals Q times V. If it's a 1 Coulomb charge, then 1 Coulomb times KQ over 3R joules per Coulomb. The coulombs cancel out, and we have joules, the potential energy of the charge at this location. So, if we have the voltage, then we know what the potential for energy is. All we need is the second charge. And then we can specify the energy at this position. Okay, so concept down, and one last thing to clarify. Now we know how to calculate the voltage at any position around a charged particle, and therefore we can make equipotential lines. In our example, we calculated the voltage at distances 1 radius, 2 radii, 3 radii, and so on from the center of the charge. And that's great for the concept, but not terribly practical. More typical equipotential lines are drawn at regular intervals of voltage versus regular intervals of distance. For example, here's an equipotential line at minus 5 volts. It's a negative charge Q, so negative voltage. Then the second equipotential line will be, say, negative 4 volts. And then where would the negative 3 volt equipotential line be? Well, if you're thinking that it should be equally spaced, maybe here, well, then you'd be wrong. Remember that voltage is inversely proportional to the distance. So, considering the voltage versus distance given that, and we see that as we move away from the charge, the voltage decreases like this. And we note how the voltage drops rapidly near the charge, then more and more gradually as we move away from the charge. So minus 5 volts here, minus 4 volts here, and then we get down to minus 3 volts out here, and way out further to get to minus 2 volts. So, to understand why this format for equipotential lines is more common, let's determine the voltage change between these 2 points, A to B. We look at our equipotential lines and we see that we're moving from minus 3 volts to minus 4 volts. So, delta V, or the change in voltage, would be negative 4 minus negative 3. 2 minuses make a plus, so negative 4 plus 3, or minus 1 volt. We drop our potential by 1 volt, moving from A to B. How about moving from B to C? Well, in this case, we're staying on the same equipotential line, and thus the voltage does not change. So delta V is 0. No work would be required to make this move from B to C. It's much like sliding a book along the top of a table. Shifting along the table's surface doesn't change its gravitational potential. It's still at the same height, or still with the same potential.